welcome to lecture 2 of CS224D. Today we'll talk about word vectors, which is really exciting because they're the fundamental Lego block that you'll need in all the other classes in the future. Also, it's exciting because you'll see a little bit of the kind of math that we're going to do. Inevitably, I will probably bore 1/3 of you to death today. I'll probably be too fast for 1/3 of you, and I'll hopefully be just at the right speed for the last third. So I will err on the side of boring more people, but making sure we're all on the same page, because right now we all think we may know the chain rule already, but once you have the chain rule in some complex beast and recursive functions with a bunch of matrices or tensors and very complex chains, you want to make sure you really have the basics right. So sorry for those of you who I'll bore, but also for those who I won't bore and for whom this might be a little too fast. Definitely it's important for the first week or two to come to the office hours, start with the problem set early, and really make sure you have the basics all figured out that we'll cover today. I had some questions already on how much natural language processing do I really need to be able to successfully complete this class. I think we will cover almost all the natural language processing sort of knowledge that you need to be successful in this class. So you don't need to already know what Chomsky tree structures are, or named entity recognition and the BIO scheme, or any of these kinds of things. We'll cover that when it comes up in the class. Are there any other questions organizationally? So the first problem set will come out next week. The office hours of all the TAs will start next week. We actually have 2 exciting new additions to our TA team. I saw David back there, was waving. And then I think we had Samip also back there on the camera. Barath, is he here today? Yeah, there he is, and James is right there. And then I think we have one new person. Is he here too? All right. Hopefully he'll be here soon. All right. So, are there any questions? Cool. All right, let's get started. Word vectors. This is a little bit of the background of why do we represent words, and what do we mean when we say we represent the meaning of a word. And meaning, again, is one of those elusive things that we're trying to capture when we try to have computers understand language. And here's just one dictionary from Webster that gives you a little bit of a flavor of what could be behind the word meaning. It could be the idea that is represented by a word or phrase. That is what we're trying to do, but it's really a bit of a cop-out because now we need to define idea, right? And then you get to thought, and before you know it, you have an hour-long discussion about the philosophy of language and thought. The idea that a person wants to express by using words, so not necessarily what's inherently in the word, but something that you're trying to express. Maybe that's a little bit easier for us also to deal with. Or third, the idea that it is expressed in a work of writing and art. Note how that is, now you have to understand what's the difference between being expressed and being represented and so on. So it gets very tricky very quickly, but fortunately for us, it will be much more concrete. So let's take just a few minutes on the history of how people try to represent words in the past and actually still do in the present. And then we'll sort of see how we get to word vectors eventually. So a common answer to how we represent words so that computers can understand them is by using a taxonomy, such as WordNet, a great project at Princeton University for many years. It's also the start of ImageNet, which all of you are familiar with who've taken 231N last quarter. Basically, it's a very large graph that defines a lot of different relationships between words. Not just is-a, but also hypernym or hyponym relationships. So, for instance, we can look here at all the hypernyms of a specific word. So in the end, everything in WordNet ends with being an entity. Every noun is at some point an entity. and then there are different tree structures. It's almost a tree. It's actually a dagger-directed acyclic graph, but for most people, they just see it as a tree. So every entity is either a physical entity or an abstract kind of entity, and then this is basically going down a very long, deep down into a tree structure. You have carnivores, and then you have basically all the way at the bottom a panda. So now one way to represent the word panda is by saying, well, a panda is a special type of procedioid, carnivore, placental, mammal, vertebrate, and so on. Maybe some you're more familiar with, some you're less familiar with, like it's an animal, an organism, and so on. So that's one way we could try to have a computer understand or represent the meaning of a word, by basically connecting it to all the other words that we have in this big graph. That works not just for nouns, but also for adjectives. So here, for instance, we can look at synonym sets, or so-called syn sets. They're basically just a list of words that, according to the people who create this taxonomy, have roughly the same meaning. But you will see here that really when you say somebody's good or honorable or respectable, these are really quite different definitions and different syn sets of the word good. So good can have different meanings, and each of the different meanings can have its own synonyms. And a good can of course also be a noun. So it can be an adjective, an adverb, or a noun. So you'll quickly see, just with the example of good, that there are a lot of issues with that. So for instance, the synonyms of good might also be adept, expert, good, practice, proficient, and skillful. But of course, each of these words, while in some abstract way they roughly mean the same thing, you wouldn't use them in the same context, right? You wouldn't say somebody is an expert versus he's just good versus he's very proficient. You use those kinds of words in different contexts, right? Proficient you would use more likely for describing the language skills, for instance. Also, you'll have a lot of missing words, because language is this evolving, beautiful beast. Beast when you try to tame it, beautiful if you just play around with it. And it's impossible to essentially keep this kind of list up to date, right? And here are just a couple of examples that basically come up. And probably this year we had invented 2 new synonyms for the word good, right? In Ninja, you might see in lots of terrible job advertisements, and maybe that's only specific to this area and certain startups and so on. So there's so much subtlety that is lost when we just say all these words have exactly the same meaning, that it's going to be tough for a computer to be able to capture that if we just say they're exactly the same. So basically these lists and this taxonomy is inevitably quite subjective, and it also actually requires a lot of human labor to create and adapt. And there's really this great taxonomy of WordNet really only exists for English. There are a couple of other languages, but none of them is as vast and well well maintained and updated as the English WordNet. And then the worst part is that it's going to be hard for computers to accurately capture similarity. So we just have basically, if we have these synonym sets, we say it's a synonym or it's not. That's just one dimension and it's binary. It's not very ideal. So generally, that is a problem that has plagued a lot of different natural language processing models that started and start with discrete representations. And that is really the vast majority still of rule-based systems and a lot of statistical natural language processing work. So for instance, when we say hotel, and we try to now, in the end of course that's still a string, but you want to give it a number. You want to assign some kind of vector so that a computer that deals with numbers can accurately represent that. And so basically what you'll see here is that this is a so-called one-hot or one-on vector that basically describes words in the simplest way. It's still very, very common in a lot of NLP systems and a lot of just generally methods that are being used in industry and in research. Basically what it just is a lot of zeros and a 1 of the index for that word. So if you have 20,000 words, you have basically for each word is represented by a 20,000 dimensional vector that has a single 1 in it. And you can give that to a logistic regression classifier, for instance, to classify a document by combining a bunch of single ones for all the words that appear in that document. This is so-called bag of words representation. Of course, you'll notice quickly that if you have a very large vocabulary, those kinds of vectors will be gigantic, right? And then you'll probably try to have some sparse representation that really only captures that index. So the one-hot representation, the main problem with it is, again, this notion of similarity. If you train a model and you say, well, I try to classify positive and negative sentences, for instance, and I see the word awesome. Now, the word awesome basically has no connection to wonderful or great. It's just a single one-hot vector. And if I try to see, well, which words are similar, none of the words are similar to one another in this kind of vector representation, right? Hotel and motel, for instance, if you just have a simple AND operator between all these indices, the similarity is 0. So that's not great. Now, the main idea of today's class and a lot of the other work is to essentially, instead of representing a word by just its own index, you're going to represent a word by means of its neighbors. And this is a very old idea from Firth from 57, who basically said you shall know a word by the company it keeps. And that very simple idea underlies a lot of old and traditional representations for words, but also the newest ones like word to vec, which we'll cover later in this class. They turn out to all boil down to this idea. So if we want to represent banking, we'll actually represent it by the words to the left and to the right of this word. So we might see already that banking and bank might both have, debt problems or something in their contexts, right? So if you now represent that one word instead of with a single index, with a bunch of indices at the very least of the words around it, you already gain something. So the question is now, how do we make these neighbors represent words properly? And the simple answer is by basically collecting with a large text corpus a co-occurrence matrix. We'll call this X. And there are basically two options of how we can compute X. The first one is we can use full documents, basically just this word, we don't care about only the next 5 words to the left and 5 words to the right, but we'll just say any word in that document will describe the current word. So these are Word document co-occurrence matrices, and what we'll gain, and we'll get into that a little bit, is essentially just general topics. If you just ignore all the word order and all the local contexts of a word, all that a Word document co-occurrence matrix will give you is general topics. So swimming, wet, boat, and ship, they'll all be kind of similar to one another because they all appear in some kind of boating topic. So we will basically lose any notion of syntax, any notion of parts of speech when we just look at the entire document as a context. But this kind of representation, which we won't go into details that much, it's called often latent semantic analysis or latent Dirichlet allocation, or different models that capture essentially a document context. They're great at capturing topics. This is about sports, this is about politics, real estate, science, things like that. Instead, what we're going to do for the most part in this class is to actually just look at a window around each word. N words to the left, N words to the right. And so let's look at a very, very simple example and actually see what traditionally one would have done with this kind of co-occurrence matrix and get some intuition of what's going on there. Here, we'll create a very, very simple word co-occurrence matrix with a very, very simple corpus. This is our corpus. I like deep learning, I like NLP, and I enjoy flying. Those are 3 sentences, and we're going to essentially build this co-occurrence matrix X now, and we will use a symmetric window. What does that mean? Sometimes people look at just the left word, the 5 words to the left, or the N words to the left. Sometimes some people only look at the N words to the right, but we will have a symmetric corpus where we basically look at the N words to the left and N words to the right. Usually N is around 5 to 10. Because these are very short sentences, we'll keep it simple, and we'll describe each word through context windows of 1 word to the left and 1 word to the right. Yeah.
How old is that context window hold up if you're inserting start and stop words? Like you just have a repetition of 5 start words, and then I guess like what is the similarity then if you look at the 4th word in the sentence, so you only have 1 start word?
So by start word, you mean often in these kinds of contexts, if we have a symmetric window and we want to describe the first word, then we might say, well, there's 1 word to the left. So I will basically have a special token S and end S for the beginning of a sentence and the end of a sentence. Here it wouldn't make that much of a difference because I is the first word in all of them. In general, that is something that you would do for most methods. Though if you use all of Wikipedia and you just have the entire document instead of sentences only, which is the most common way to do this, the start token doesn't make that big of a difference.
I guess I was wondering, like, in terms of, because you can chain adjectives before an object, and so like depending on your vocabulary, you can end up in a weird situation where you might have multiple start words for one object, but almost none for another object that is synonymous, just because that other object in your training vocabulary was preceded by a bunch of adjectives.
That's right. So in general, what we will observe is that training word vectors will hugely depend on the corpus that we'll train it on. So, and if your corpus is not representative of language overall, you won't get good word vectors out of it. So here, this one will have, for instance, no connection to we or they, right, or other pronouns. It only knows I. And so that's step 1 for a good corpus. It should have the words that you like to describe in it. But then even once you have them only once or twice, that's also going to be tough statistically. So we will run into that problem. The sort of default solution is to just use Wikipedia. If you use, as long as you use Wikipedia, it's actually a really great corpus to start learning these word vectors. And that way you have fewer of these problems, but in general, the more the better. So the largest word vectors that we've trained in the NLP group, I think it's still correct, as a project with Jeffrey Pennington, Chris and me, we used Common Crawl. It's basically a way to download almost all the websites that allow you to be downloaded, and just you have a gigantic 840 billion token corpus. So tokens is basically word instances, and that has a very large vocabulary, and that works even better than just having the, in comparison, small Wikipedia. All right, so let's build our matrix. So the example corpus is above here, and now all we do is very simple. We look at each word, and we basically look at how often each of the other words appears to the left and to the right of the current word. So I basically has like twice in its window and enjoy once in its window, and that's it. And like appears in its window has twice I and once deep and once NLP. Yeah?
I was wondering for larger windows, so do they usually use just like the 0, 1 kind of thing, or is there like a kind of decay function based on how far?
That's a great question. So you might say, instead of giving 1 to every word in my window, I actually give 1 to the first words to the left and right, and then half to the second words to the left and right, and so on. And that is actually a technique that can help some of the word vector representations. We'll mention it briefly in a couple of slides, but yeah, it's a great idea. Especially if you have 10 words or so, the 10th word to the left might not be as relevant. Yeah.
Is there a token for like starting a sentence? In this case, like all the I's you have, and some token for start of sentence, start of text?
That's a great question. And yes, sometimes you do use it, and it can help. But the larger your corpus is, and the longer your documents are, the less it matters. So here, we could have done it, just kind of made the table even larger. But yeah, definitely like start and end token of sentences are commonly used for smaller corpora. Great questions. All right, so this is basically one way to represent words as vectors, right? This is already it, right? It is a list of numbers, and now we at least would have certain things such as like and enjoy at least have some overlap if we just kind of did a simple inner product or a simple logical AND, then like and enjoy would be more similar to one another than enjoy would be, for instance, to deep. Right? So we captured that liking and enjoying might be actually more similar. So that's something. It's an improvement over just a single one-hot representation. But of course, the problem with this is that now our vectors increase in size with the vocabulary, which isn't ideal. Right? We have a new word in our corpus, and now we have a new column in this matrix and a new row, and we have to update the whole matrix. So that's not ideal. Also, we'll have a lot of words, so that matrix will get really, really large. Think of Common Crawl, 840 billion tokens, millions and millions of different words. You wouldn't want to have to install that on every time you install your app that uses some deep learning or some other algorithm on your phone, like have to carry that gigantic matrix around. And basically, that kind of matrix is still very sparse, right? So every classification algorithm that we'll use on top of it that may eventually have to learn a weight, an importance weight for each of these different dimensions will have a tough time. So the models that you'll train will not be very robust. So the solution will be to use low-dimensional vectors instead. So the idea is that we're storing only the most important, and again, this is a little bit with scare quotes, the important information in a fixed small number of dimensions. And that will essentially give us a dense vector. And I won't go into, we'll go into some details for the dimensions, but in most cases, the dimensionality will be between somewhere between 25 and 1,000, which is a pretty large range. In most of your applications and your projects, you're unlikely going to need 1,000-dimensional word vectors because you won't have enough training data. To train these kinds of models, you need huge machines and so on to do that. So if you just train a simple, small data set with a couple of thousand of examples, you usually can get away with 25 or at most 100-dimensional word vectors. So the big question now is, how do we reduce the dimensionality of this matrix X? And the first method, which is quite common, is to use singular value decomposition, or SVD. Can you raise your hand if you're familiar with SVD? All right, excellent. All right, great. So basically, we just have here our orthonormal columns. We have our singular values here, and they're sorted by the first ones in the top left. And basically, we know that each of these columns basically describes sort of or reflects the principal components here, the axis of the greatest variance of your data sets. And now what we can do is, instead of representing X with all of the orthonormal columns and rows, we can just take the top K. And that will essentially allow us to reduce a lot of the noise in this representation. And also now we can fix K and say, no matter how many more numbers you get in here, we will only take the top K eigenvectors, principal, orthonormal columns. So let's actually look at what this would mean if we implement it. It's very simple to implement this kind of model. Again, same corpus. I just basically created a simple array in Python, and we just run SVD on X. And we basically get here our orthonormal columns, our singular values, and V. And now we can represent and project this by taking only the top two biggest singular values and corresponding orthonormal columns of U here, and basically plot the text and plot the words in these two dimensions. So again, we have a simple, very simple co-occurrence matrix. We just apply SVD and take the first two orthonormal columns here, or the left singular vectors. And already, we just created a word vector that captures in some low-dimensional space some of the relationships. So for instance, like and enjoy or close by, I being the only noun or the only subject of these sentences is by itself. NLP and deep and flying are closer to one another, flying and learning are close to one another, and so on. So already, with this very simple corpus, some very straightforward relationships are captured in our word vector space now. And now n here is 2 dimensions, and these 2 dimensions capture some of the information we would want. Any questions about using straight up SVD and co-occurrence matrices? Yeah.
What are the axes?
Sorry?
What are the axes?
Oh, these are basically just when you look at your orthonormal columns U, there's no specific meaning to these axes. That's just where the numbers come out to be. Yeah.
So like and enjoy should be relatively similar, but it seems like is kind of way out there because it's in every single sentence.
Right. So we can look at essentially like has, and this is actually a good observation, it actually appears quite a lot, and it has the most words in its window. And you'll notice that that's probably not ideal, right? We'll actually have some hacks to deal with exactly that problem in a couple of slides. So it's a very, very good observation. Yeah.
Yeah, in examples with more data and more dimensions, do we have any intuition on what these dimensions correspond to in terms of word meaning?
So very rarely can you find that a single dimension by itself will have a great meaning of like, oh, these are only things that have a very high value are objects and not verbs or something like that. In most cases, the meaning will come through multiple dimensions only, and through the relationships and bases vectors of that entire space. So yeah, so we already observed that just because like had a lot more values in its row, it kind of made it more special than it should be. So the frequency of the words mattered a little bit. But basically, we got somewhere, right? We now have one way, it's a very simple way, to get dense vector representations for every word. And this is going to be for all the subsequent models we'll use, all the deep learning models. That's how we're going to represent words. We're going to find better ways to compute this vector, but that's essentially what all these different methods will capture. Co-occurrence counts, words to the left, words to the right, projected into some lower dimensional space.
What is this 2 dimensions?
So 2 dimensions is a good question too, only for visualizing the vectors. In almost all cases, they will be higher than 2 dimensional. They will be 25 at the very least, up to 1,000.
You determine the 2 dimension based on, like, for example, how the singular values decay?
Yeah, exactly. So these are the top 2 dimensions corresponding to the top 2 largest singular values. Yeah.
No, I mean, like, for example, if there's an energy criterion, for example, in trying to...
Oh, to cut off the singular values? It's rarely ever used. It really... We're getting a little ahead, but it's a good question. So how would you make this decision now, how many dimensions you should use? This will come up over and over again in your class projects. You're going to get extra points if you do this properly, and you're going to lose some points if I see certain graphs where you have a hyperparameter, for instance, one that you will very often optimize over, which is number of word vector dimensions. And if your graph goes up like this, and then you end, I say, in my feedback, well, why didn't you run it with even larger, right? Maybe it would go up even further in your accuracy or something like that. And so the best answer to how many dimensions should you use is determined by your overall task. And we don't know yet any overall tasks we could do, such as named entity recognition or sentiment analysis. Those will come later in the lecture. So right now, we'll find simple intrinsic evaluation metrics, which we'll cover in a couple of slides. Yeah.
By representing words as vectors, don't we impose, I guess, some kind of transitivity? So like A is opposed to B, and B is opposed to C, then A is also somewhat opposed to C.
Yeah, so if you have a proper space, then that will be the case. And we will see lots of interesting relationships that will come out of exactly those kinds of similarities.
Because it's not like a bad thing. Because I mean, it's not always the case that if like is similar to some other word, like you don't always have that with words. But
That's right. So, but you're also fortunately not going just in a single directions when you compute these similarities, right? You can have various distances and things like that. And the distances, you can also, when you try to understand the geometry of the space, you can make them directed. So it's not just like a similarity, which is undirected kind of distance. So, but in general, you're right. There are a lot of problems with capturing or with representing words as a single vector, right? We have words that there are polysemists that have multiple meanings, right? Good can be the goods that you buy in the store. It could be an adjective. It could be an adverb. Can have different meanings. Bank could be the sandbank, could be the money bank, so it could be the bank you're sitting on. So there are issues with word vectors, and there are also people who try to deal with those issues, such as learning multiple vectors for each word. And you have bank_1, bank_2, bank_3. So we had a paper of Eric Huang, Chris and me, about just that, like learning multiple word vectors. And so there are lots of issues, there are lots of fixes, but in the grand scheme of things, just having a single vector for each word will get you very, very far. And it's what you almost always have to do for your projects. Or it's enough to just do that. There are also other problems, such as sometimes you might say, so if you ask, for instance, some people in one country how similar they think their country is to that other country, they might say, well, we're similar to them, but then other people might say, but they're not similar to you, right? So you can already make this fail, the kinds of geometric representations for single words with just two words by themselves, not even relationships. So lots of issues. But in practice, and that's kind of why we defined that in the beginning, we're going to try to make computers understand language to solve a real task. And for those kinds of real tasks, this is a great representation. All right, so from now on, every word will be a dense vector for us. So we already had this very cute observation that like, which had a higher frequency, turned out to be somewhat special and by itself in this space. And this is actually a problem that people observe a lot and have essentially fixed by saying you have a maximum value for the counts. So there are certain function words or so-called stop words that are very frequent, but rarely ever add that much to the meaning. So the, he, or has are very frequent in a corpus and basically just capture syntactic information, grammatical information. And so there are two fixes. One is to just ignore them all. You just delete all the words from the corpus. That's one way. I think a slightly better way is to basically say you take the minimum of the actual value that you have in each cell, in each element of your matrix, and some maximum value like t equals 100 or so. And with that, these stop words or function words will not be that special. And then another great idea that already came from you guys too is to have a ramped window where closer words have a larger count. And you basically give fractional counts to your word matrices. Sorry, to the co-occurring words. Instead of just taking the counts, you can also actually compute correlations between words and then set negative values to 0. There's a lot of work. Once a paper from Google came out a couple of years ago by Tomasz Mikolov, a lot of people got really excited about word vectors and started doing all kinds of really great analyses. And next week we'll capture just a couple of the details of word vectors, but we're still just doing an overview. So let's look at what you can capture when you just use a simple kind of SVD on some somewhat massaged count matrix. The first one is that we get very interesting semantic patterns in terms of very simple inner product distance. So you basically just look at how close are two words in this resulting vector space. And then you can group them, very simple binary tree, and amazingly it does find that wrist and ankle are the vectors closest to one another. And shoulder and it comes next, and then arm is the next closest, and so on. So you can basically build these similarity trees, and they already capture an amazing amount of what we would think is kind of world knowledge, right? But again, there's no magic here. wrist and ankles are probably appearing in similar contexts. You can sprain them, you can break them, they're close to your body, they might be mentioned in connection or in co-occurrence windows with athletes and things like that. So no magic, but still kind of amazing that we're capturing all these semantic similarities. Here's another interesting observation where we again project down these word vectors. Sometimes you can use PCA for that. Sometimes you can just look at the first two orthonormal columns of straight up SVD. But basically you can see also that different temporal expressions for different verbs are actually close to one another. So show, showing, showed, and shown are close to one another in the vector space, and grew, grow, and grown are also close. So it captures also some temporal aspects of language. Here's another interesting semantic pattern, such that a verb and a noun of an agent that is most likely going to partake in that kind of activity is essentially in an interesting linear relationship even. So drive minus driver has a similar sort of direction as swim and swimmer, or learn and student, and teach and teacher, treat and doctor, marry and priest, or pray and priest, and marry and bride. Right? And this is from over 11 years ago. Yeah.
What is the input of this vector?
What is the input of those vectors? So it's the co-occurrence matrix that we started out with. We take a very large corpus, and then we compute the co-occurrence matrices, run SVD, and then visualize it in 2 dimensions.
So you should eliminate all other words just to say it's correct.
We eliminate what?
Other words.
Oh, yes, that's right. So for a lot of these visualizations, if you mapped all the words of your vocabulary into the space, it would be very hard to visualize. All the words would kind of be overlapping. It's just very hard to visualize. But you also won't see as many beautiful kind of relationships. It's a good question, yeah. Yeah, so for these kinds of visualizations, you often only project a subset of the words into your lower dimensional space. There are some visualizations also that try to do that with many different words, but then it's harder to see interesting linear relationships.
Do you manually choose a subset of words or do these are
Yeah, so here they did choose that subset. Though there are also some visualizations where you take 100 or 2,000 words, and then you can zoom into the space. You just create a very, very large image, and you zoom into the space, and you still see some relationship. So they're not like totally cherry-picked, but not always do these kinds of relationships work. Like again, if you have something where you have a very polysemous word, then it will only have basically the majority meaning, the meaning in that corpus that you trained it on, where that meaning appeared most frequently. That's the kind of meaning that will have the nice sort of linear relationships as you project it down. Yeah.
Just out of curiosity, did anyone do analysis of whether this is statistically significant?
There will be a lot of statistical analysis that we'll get to, where somebody created a data set, also Tomasz Mikolov from Google and co-authors, where they essentially took thousands of examples, currencies of countries, country names, and then tried to basically find linear relationships. Like, and again, this is temporally different, like Germany minus Deutschmark plus US dollar goes to United States, things like that. So there are different ways. Now, it's not quite statistical significance, but they basically created a data set that had tens of thousands, because you can kind of artificially create all the currencies, all the temporal expressions like show, shown, shown, and so on. And then you can compare a lot of the different relationships in at least significant kind of way, where you evaluate and you say, oh, my method got 80% of all of these relationships correct.
So how do you update the word vectors if you have to, so your co-occurrence matrix can be very large, right?
Right.
So as language changes, do you want to update your word vectors?
That's right. So that is exactly what we'll describe in the next slide here, which is there are some problems with this. So what happens when you add new words or new documents, and now you have to rerun your entire SVD. Now, I think there are online versions of SVD, so that's one way to solve that. But in general, for running proper SVD, you're going to have a huge amount of cost for very large matrices. So if you have millions of words, millions of documents, SVD is not going to scale very well. It will require a huge amount of RAM. And yeah, it's very hard to incorporate new words. You just got a couple of new Wikipedia articles, a couple new words, but you really want those words to be in the space of all the other words. Now you may have to rerun that full SVD. And also, the SVD optimization is going to be a very different learning regime than all the other methods that we'll see in our deep learning models. And so we'll actually not use SVD for most of our techniques, and you also won't have to implement it in your problem set. Instead, what we'll do is we'll try to directly learn low-dimensional word vectors based on just single windows. And then we might go back to SVD and see if we can learn from both of these kinds of models and combine them. So basically, it's quite an old idea, but there are a couple of papers that are quite relevant for this lecture. So the most relevant one, which I'll also encourage all of you to read, is NLP Almost from Scratch by Colbert and Weston in 2008, and in 2011 they had a journal version. I think it's listed in the syllabus as well. And then the most recent, even simpler and faster model is the well-known Word2Vec by Tomasz Mikolov and other folks, and that's the one we'll describe right now in all its gory details, because it's really nice, very simple. We can get our hands dirty with a little bit of math on the whiteboard and start thinking about how to take derivatives, how to update them with SGD and things like that. All right, so the main idea of Word2Vec is, instead of capturing all these co-occurrence counts directly, we're just going to predict surrounding words of every word. So instead of collecting a large co-occurrence matrix, we're just looking at each example one at a time. We're going to say, in the current window, based on my current center word, can I predict the n words to the left and the n words to the right? Because it's hard to draw something. Yeah, that's basically the main idea. It turns out that idea of predicting the words to the left and predicting the words to the right will eventually also capture just co-occurrence statistics, just like the previous method. But it does it in a very online way. I can easily add a new word, run it over that word, and update the model. And yeah, it's very easy to add also new words, new sentences, and so on. So let's look at the objective function of Word2Vec. And we're going to drill into this quite a lot in the next half hour. We'll define again our co-occurrence window. We'll say here the window has length m. So for each word, I will try to predict the m words to the left and the m words to the right. And we're not going to use any of the hacks of weighting them differently for now. And what we're going to try to do is to essentially maximize here the log probability of any context word given a current center word. So we have a very large corpus of T tokens. Could be 840 billion. It's going to be tough, but it'll take a very long time. And we go each word one at a time, and for each word that we have, we're going to go m words to the left of that word and m words to the right. And for each of those context words, we're going to try to maximize some kind of log probability here of that word. And theta will be all our word vectors that we're going to try to jointly optimize. So let's look into how we could represent, in the simplest, cleanest way, the probability of a context word given the word in the center. So I will describe here O as the outside or output word ID. So again, that's just the context word, the outside word, but context is not a great word because C is going to stand for center. So the outside word ID, we're going to try to maximize that probability, conditioned on the current center word. And the way we will do this is with this relatively simple expression, where we just have an inner product here and the exponent of that. So just get positive number here. And we'll have a vector u for the outside word and a vector v for the center word. And I will use U for always the outside words. And so this is already an interesting observation here, which is every word will have two vectors. One vector when we represent it as an outside word, and one vector as we're trying to predict the outside words. So I think it'll be good to show you. How can we get the screen up? Oh, magic. All right, thank you. So just to walk you through the process, we're going to have a bunch of different words in a corpus, like I like this class and so on. Each line here will represent one word, a one-word vector. And let's say for simplicity for now, we'll have a window of 2 words to the left, 2 words to the right. And so we're going to start at this word and basically try to predict this word and that word and then this word and then that word. And once we optimize for this window, we will move one to the left. And now this is our center word. And now that center word will try to predict this one, and that one, and this one, and that one. And so we're basically going to move this window one word at a time and try to maximize this probability. All right. Now we have to go back down. Sorry, we're going to have to do that twice. Yes?
You mentioned having 2 vectors per word because you want to distinguish between the input versus the predicted. Why not represent the input as a vector? Because that's really what it is, right?
The input is also a vector. Sorry, the input is a word vector and the output is also a word vector.
No, I mean like it's going to be a vector of 2 words, right? Because you've got n words right?
Mm-hmm.
You can change that formula so that C is actually going to be, or I guess it would be a vector.
Yes, you could try to represent all of the vectors you're saying at once in each window. You could do that.
And then you don't need 2 separate vectors per word anymore.
To be honest, you don't need 2 separate word vectors in general, right? We could just have all the vectors be V, and then you just have here a quadratic expression inside. It turns out that having these 2 vectors is just basically going to make your optimization easier. And this is not very beautiful, but in the end, in order to capture as much as you can of all the statistics, you're just going to average or concatenate these 2 vectors to represent each word. So at the very end of this optimization, after we basically learn 2 vectors for each word, we're just going to average the 2. Not very beautiful, but works incredibly well. All right, so this is going to be our objective function for each single window. And we'll derive basically the derivatives and all these in 2 slides. But before that, just on a very high level, once we have computed here our entire objective function, we want to optimize this. And the way we're going to do this is with very simple gradient descent. And who here is familiar with gradient descent? Excellent. Most of us have all the prerequisites. But just a very simple refresher, you're going to have some function that won't ever look as beautiful as this one in deep learning. You have a derivative, and you will just basically start at some random value. So we will initialize all our word vectors at just small random numbers for a very large matrix. Usually we call this d-dimensional, and you have n many different word vectors. So you start out with a very large matrix with a bunch of small random numbers. And then we're just basically computing a derivative and then updating with some step function based on that derivative all our word vectors. So here this is just obviously not the kind of function we're using, just to basically show you gradient descent, which is what we'll do. Technically we'll do stochastic gradient descent, but we'll get to all of those details later. All right, now let's do a quick refresher on gradients, and then we'll actually derive on the whiteboard in 2 slides the gradients for the objective function I just projected on the board. So the first and most basic of the Lego pieces are the derivatives for just a single vector. Hopefully these are familiar, but might write it out. So if generally you're in doubt, it's always good to write out the indices. So maybe, sorry, if you can just put up the board like a little bit, not all the way, thanks. So generally, if you try to get the derivative of, that's perfect. Can you stop? No? All right. So x transpose A, derivative of x. If you're not certain, and for this it's very straightforward, you can just write out A. But eventually we're going to have lots of matrices, and it's much more complex. And so sometimes it's helpful to actually write out what the inner product really means. So here we just have xi, ai, and I equals 1 to the dimensionality d of those two vectors. And this is the part where I'm going to bore 1/3 and sorry, bear with us for this lecture. Basically now we can look at the derivative for each of the elements of the vector. And then we basically see, okay, xj only appears in one of these elements, so we just have the derivative with respect to just one element of the x vector xj is just aj, and then we can compute basically here our vector for each of these. So the first element will have this as its value, the second one will have this as its value, and this seems very trivial if it's just two vectors, but once you have gigantic matrices or tensors, it can help sometimes to write this out. And so on, all the way to an, and that's how you'll then see that this is the right derivative. And sometimes when we basically take these shortcuts by just knowing what the derivatives are in matrix notation, but you feel like, oh, that wasn't quite intuitive, it can be helpful to write it all out with the indices for each of the elements of the matrix, and at some point you gain like an intuition of like, oh, this makes sense overall. So maybe instead of going up and down again, I'll just write out some of this stuff. So let's make sure we get the same notation. So let's write, for instance, a function that is a little more complex and do a little refresher on the chain rule. So y, the f of u, and this is the same notation, u equals g of x. And we may have some complex function that basically combines these and says y is a function, or y is defined as f of g of x. And now we want to take the derivative. I sometimes use d, so dy dx. I also often write delta partial of y, partial of x. And that will just be what? Quick refresher on the chain rule. We have a function here we define as y, and we have want to get the derivative with respect to x. Say again?
Partial y, partial u.
That's right. Times? I think that's what you said. That's exactly right. All right, so that's the chain rule in its abstract form. Now let's make this very concrete and start out with a simple example, and then we can do it with a much more complex example. So let's just define our function y here as y equals f of u equals 5u to the power 4, and our function u equals g of x equals x cubed plus 7. So for a simple function that basically we're trying to compute now y dx of putting those two together, 5 times x cubed plus 7 to the power 4. Right? And now that looks much more familiar. And now we will basically define here our different elements. So we can define this here as our u, right? And now we can just write out dy du. So what would that be? Can you raise your hand? U what?
Cubed.
That's right. All right. So straight up derivative, assuming this is just the function. So here, this is our simple function. Now let's do the derivative of u with respect to x. So that's just this function.
3x squared.
That's right, 3x squared. And now we basically can combine both of these, and we'll just basically multiply both. And so we have dy dx, or partial y with respect to x, equals 20 times u. We can put in u again, plus 7 to the power of 3 times 3x to the power of 2. We can simplify that, but we don't need to. All right, so that's just straight up chain rule with a very simple function. Any questions on that? Great. All right, so now let's do the actual function of word to vec, or the simplest version of word to vec. Nope. No, we'll stay on the whiteboard. Sorry. All right, we have here our log probability of P of O given the center word, and these are just word IDs. And our formulation for this function was to have the exponent of a vector u of the outside word transposed times VC. And then we normalize this with by going over all the word IDs of small w to capitalized W of the exponent of u W transposed VC. And if you're familiar with logistic regression, you can kind of see this as a dynamic logistic regression, right? These are our weights, and we have a probability for each of the potential classes W, right? And one of those is O. All right, now generally what we'll do is we'll actually take the log probability, log monotonously increasing function, so the argmax of whatever we have in here when we optimize this is the same as when we optimize the log of that function. So now let's basically take the derivatives of this with respect to VC. All right, now we're going to make this a little interactive so that we don't fall asleep. So what would be the first thing we might want to do to simplify this function, given that we now have the nice logarithm of this fraction? Yep.
Split into a difference.
That's right. So we can now, right, we're not taking any derivatives yet. We just basically split this into difference of log of exponent of UO transposed VC minus the sum over W equals 1 to W of exponent UW transposed VC. Oh, right. What did I miss? That's right. All right. Now we can see this part already simplifies, and we basically just get this portion here. Now the derivative of a sum is the derivative of the summand, so we can just basically take both of these and separate them out. So we can write derivative of VC of just UO transpose VC minus derivative of the log of the sum All right, now this one we already know. So that's just u o. So basically, we have u. We'll remember that. And now let's look at this beast here. And let's not remember the minus in front of it. So what could we do next to take the derivative of VC? Well, we see here something that looks like a great application of the chain rule, right? Because we have a function f, so we can define the log as our function f, and we can define this whole sum here as z, which is a function g of VC. And now this is where it is really great to know the chain rule in all its gory details. So now what we're going to want to do is take derivative with respect to VC of f of g of VC, right? And g again was our z. So what's that in abstract? Well, let's just write it out abstractly. So we have what? Just chain rule like definition almost. That's right. Times derivative, and we just call this f of z, times the derivative of g of VC times the derivative of VC. That's right. All right, now we already heard the first one, which is derivative of f of z with respect to z, where we can basically, we know f of z is log, and so we also know that derivative of log of c with respect to z is what?
1.
That's right. So what we can write here for the first part is simply, since this is just simple function f, it's just 1 over whatever z was. Now z we nicely defined as just this whole sum. So let's just write out what this sum is. So again, w equals 1 to capitalize W of exponent of uw transpose times VC. All right, now times the derivative of g of VC with respect to VC. Now g of VC is this sum, so let's write it out. VC of this sum, W1. Now, first, really easy to mess up point here. We don't want to use the same index twice. So let's have a different index here. Let's call it x equals 1 to capitalize W of exponent of uw transpose VC.
UX, right? It's a GT index.
Oh yes, perfect. Thank you. All right, does that still all make sense? All right, then.
Does the index matter? You're still doing the same sum.
So it will matter. It will matter quite a bit. Yeah. All right, so now we're just going to take the derivative of this sum. So let's maybe write that out. So let's look at this, number 1 here. And so what can we do to simplify the derivative of the whole sum? That's right. So we'll take it inside. So we're going to have the sum So this equals the sum of all the derivatives with respect to VC of x equals 1 to w times the exponent of ux transposed VC. All right, now we'll apply the chain rule again here. What's the derivative of the exponent of something? That's right. So we can rewrite this as x equals 1 to w of the exponent of ux vc transpose times the derivative of the inside. So this is derivative of vc with respect to ux transpose times vc. And that's again something that we did already right here. So what's this? ux, that's right. All right, so now let's put it all back together in one equation, all the different pieces we just computed. So we basically have the whole derivative with respect to VC was UO, the very first part here, minus the sum of, and now this is where it's important that we have x and w. So this sum over w is outside of this sum, right? So we have here now the sum over x equals 1 to w times the exponent of ux transpose vc times ux, our final vector here, so this part of the sum. And then what we could do also, instead of multiplying, now technically what we would do, and I'll just write it out, is this times 1 over the sum that we have with w equals 1 to w of the exponent of uw vc. But we can now pull this sum in and multiply each of the elements of this sum with this one. That's why it's so important to keep the indices separate. So let's multiply, again, this is just this part right here. We're going to multiply this with each of the elements of this final sum. So we have UO minus the sum over x equals 1 to w times the exponent of ux transpose vc divided by the sum of w equals 1 to w of the exponent of uw transpose vc.
Seems like moving it inside just makes the computer have to do more work. Like,
it's a great question. So what do we observe from having done this now? When we looked at the very beginning definition of the conditional probability. That's right. It's still sort of a softmax, kind of a dynamic one with these vectors, but it's basically the probability. And we dropped something very important, which is the ux here. So basically, we can rewrite this as u of o minus the sum over all our word vectors, or word IDs, of the conditional probability of this x given this c times this ux. Right? And in general, and this is something we'll get to now in the problem set a lot, this is a very, very expensive function to calculate, right? Because this capital W could be hundreds of thousands or even millions large. But these are basically all the mathematical tools you'll need to do problem set 1 of the math. And then we'll actually come up with much more efficient ways to avoid having to have this entire normalization. And what we might do is just have a very simple binary problem of saying improve the probability of these two being on. Yeah.
But wouldn't we have already had to compute all the terms inside that sum when we did the forward pass to output the probabilities?
That's right, but even that forward pass is too expensive. We're going to try to avoid at all costs summing over the entire vocabulary at each window. Imagine you have millions of windows, and now you multiply that with millions of, like a sum over millions of elements at each of the millions of windows. It just doesn't work. So this is the simplest way. Now, nobody would actually implement it exactly with these equations, but intuitively, we just went over this to understand sort of what the equations look like. So can we pull the projector back down, please? So really, this sum will be too expensive to compute, and hence this whole objective function is not scalable. And we already observed that very well. So what we will do is either approximate this normalization constant or define negative predictions where you only basically sample a few of the words that do not appear in the context. It's very hacky, but in deep learning land, nothing has to actually sum to 1, right? All we care about are these word vectors in the end. Whether you actually get a really nice probability that sums to 1 is kind of irrelevant. You're just trying to capture the co-occurrence statistics. And it turns out that if you have millions of words, most of the words don't appear in any given other words context, right? If you look at zebra, the fact that zebra doesn't co-occur with toaster, TV, you know, laptop, like it doesn't, none of these words give you that much additional information. So what we will do, and what you will do in the problem set 1, is essentially focus on mostly the positive correlations and just randomly subsample a couple of the words that don't appear. And so I think we have 7 more minutes. So let's go a little bit into what kinds of amazing things will fall out once you are able to optimize this function very efficiently. These are basically the well-known analogies that happen to fall out of these low-dimensional vectors. So for instance, there are syntactic grammatical relationships of singular and plural. So the vector difference between going from the vector, now again 100 to 500 or higher dimensional, of apple minus the vector representation that we learned for apples is similar to the vector direction that we get of car minus cars or family minus families. So what's being captured in these co-occurrence statistics, and again, it's not very intuitive why predicting the words to the left and to the right captures the statistics of these words to the left and to the right, but there's some interesting work that we may touch upon a little bit next week of why this actually happens. But again, there's no magic here. The main idea is that it turns out when you subtract some of these statistics from that happen in plural words, they happen to be similar. There are more other, you know, like the word multiple, for instance, or several, or a couple, right? These are all words that might appear in the context of plural words. And now you projected it all down, and it's now in the lower dimensional space, not really in the whole high dimensional space, but you still capture that you're taking out all these other co-occurrences when you do compute these subtractions. You also get interesting similarities and geometric relationships for verb and adjectives, such as, you know, shirt minus clothing is similar to chair minus furniture. So what we described in the taxonomy originally, where you had to very rigidly define this is a subtype of this thing, it turns out it's kind of in the vector space that we learn just by basically projecting co-occurrence statistics into a lower dimensional space. And this is very surprising to a lot of people, and they think, oh, the model knows and learns and understands, but it doesn't. It doesn't do any of these things. It's just basically co-occurrence statistics if you train it with the right corpus. And this one is one of the most popular ones, and also the prettiest ones of the data set from Google, where if you take the vector of king, you subtract the vector of man, you get something similar to the subtraction of queen and woman. Again, just from having low-dimensional co-occurrence statistics. Yeah.
It seems like when you when you run a forward pass through word to vec with a word that it hasn't seen during training, it should project it in a similar point cloud cluster.
So as you run a forward pass with a word that you haven't seen during training. So the default thing just in practice will be that you just have an UNC token and nothing happens at training.
Wouldn't it?
Sorry, do you mean at test time or at
No, like
training?
I guess I'm trying to draw an analogy to like how would this perform without the absence of with the absence of smoothing, right? If you're doing kind of smoothing during your training, it should still recognize the surrounding words around that unknown word, and it
That's
should
right.
still project it into a similar area as it's like syntax.
That's right. So as soon as you train and you project and you say, now in order for me to be better able to project these context words, you immediately will update with stochastic gradient descent the word vector for that center word in order to make it be more likely to predict the outside words, hence more likely to capture the right kind of statistics if you do it a lot of times.
But have people evaluated how this performs with respect to like traditional ML, NLP algorithms?
Yes.
Smoothing to predict unknown words?
So I don't know about the unknown words. Usually all these methods work better the more words you have, as long as your corpus can allow it. I can't think of any specific unknown word evaluation, because basically you just say the words that I rarely ever see are just getting the UNC token, and that's one vector for all the unknown words. That's usually how most people deal with it in practice. But what people have done is actually now went back after seeing these beautiful results of king minus man plus woman goes to queen, and understand how do actually these new methods relate to the traditional PCA or SVD kinds of methods. And both of them have actually some advantages. So when you look at SVD or various other methods like it, they actually train quite quickly. They require a huge amount of RAM, but they are quite fast. And they make very efficient use of the statistics. Instead of collecting statistics and optimizing a function one element at a time, you just can collect it once, and then you can run immediately on the statistics, which is an advantage. However, they primarily used to capture just word similarities, and they didn't have any of these beautiful linear relationships of king minus man plus woman going to queen. And they used to give disproportional importance to these large counts. Of course, that though is a way, there's a way you can fix that by just having a cap on those counts. Whereas the skipgram or word2vec kinds of models, so word2vec is kind of a summary term for multiple different methods, skipgram and continuous bag of words. You actually can implement both in problem set 1. Continuous bag of words is very similar. The main differences are sometimes you can compute or predict from the center word the surrounding words, but you can also go the other way and say from the surrounding words I want to predict the center word. So it's not that big of a difference. But basically, those scale with the corpus size, which is not great, right? If you add a larger corpus, you now need to go over many more windows. And they make very inefficient usage of the statistics. You just kind of hope that after running it long enough, you capture overall the statistics of the data set. But as we've seen, they have these great performance improvements on a couple of different tasks and capture these complex patterns that go beyond just these two things are similar. And I guess we're running out of time, so maybe in the next lecture we'll look into a method that will actually combine the best of both worlds. It'll run something like what we've seen here, but there are no more exponents needed. It's a very simple function, and it will actually run that function over the co-occurrence matrix elements instead of over each window at a time. And then we'll have the best of both worlds. All right, see you next week.